Hello everyone, in this video I'm going to explain the design of a distillation column. So first of all we will be going through like problem statement. So it is a binary system consisting of benzene and toluene. So feed consists of like 40 mole percent of benzene and it is containing 50% quality that is flashed. So the top product basically contains majorly benzene and toluene is about 2 mole percent, and feed flow rate is 100 kilomole per hour, and feed pressure is 1.2 atm. So also condenser pressure and boiler pressure is also given. So reflux ratio which we will be using is 3. So we basically need to design the distillation column. So for that we need a number of stages and column internal design. So for this purpose we first of all need to design, get the information like minimum number of stages, actual number of stages, and the feed point location. So for this purpose we will be using a shortcut design method in the Aspen Hysys, and using that information we can design the distillation column through a rigorous method. So let's straight jump into the Aspen Hysys. So here you can see like in the message we need two components. First of all we need components like benzene and toluene, and secondly we need the fluid package like equation of states which are needed to solve for different physical properties. So we can go to component list. So from there we can select our components which are benzene and toluene. So let's search about the benzene. We can type the full name, or we can go this way in the tab like search by, and we can select the simulation name, we can select the formula. So I'm going with the full name, that is benzene. So either you can double click it or you can select it, and then you can press the tab add, and it will be automatically added to the this data bank of the Aspen Hysys. So second component is toluene. So this in this way you can add both of the components, and then we can move to the fluid package, and by adding the add tab, and then we can see like there are many number of fluid packages. So every fluid package is like specific regarding to the components. So for this time being we are moving with the Peng Robinson. So we can select the Peng Robinson. So we can see like everything is okay. So we can move to the simulation tab. So if there is some problem in like compatibility of the fluid package with the components we selected, so Aspen Hysys can show warning, so we can change the fluid package and then accordingly. So now we can move to the simulation. So here you can select the stream, like material stream is like indicated with the blue color, and the energy stream is indicated by the red color. So we are moving with the material stream. So by double clicking we can rename it, like we can give it name as feed, and then obviously we know that it is 50% flashed, so vapor fraction is like 0.5, and then we know the feed pressure, that is 1.2 atm. So here we have a lot of number of units, so it can automatically convert from the given units to the SI units. So we can select here like atm. Okay, so then we have the flow rate like 100 kilomole per hour. So from here you can see like it is showing the message like composition is still unknown, so we can move to the tab of composition, and then we know that benzene is in the field is 0.4, that is 40 mole percent, and we can see like here the mole fraction, we can select the mass fraction, we can move to the molar flow rate, mass flow rate. So based on the given information we can select any information. So like we know that overall fraction is 1, so we know that remaining fraction is for toluene, so we can take it as 0.6. Okay, so everything is okay. We can see like here it gets green, so it is showing the message like okay. So material stream color is also changed from the light blue to the dark blue. Let's move to the equipment. So we have many equipments here, we can see heat transfer related equipments. We have manipulators, we have piping and hydraulics. So we can move to the separator. Here we will find the shortcut design method, so we can drag and drop here, and then we need to double click it, and we can rename it anything like DIS TIV, and for the inlet we have like field, and for the condenser duty we can name it as Q_C, and for the distillate we can name it as DIST, and for the reboiler duty we can name it as Q_R, and for the bottoms we can name it as BOTT. Okay, so we have here specified like top product will be in the liquid phase. So everything is done. So now it requires the key component information, so we need to move to the parameters, and here we will find the light key in the bottoms and heavy key in the top. So we can define here like heavy key in the top is the toluene, and its mole fraction is 2%, so we can take it as 0.02, and the light key in the bottoms is obviously the benzene, so we can take it as 0.02 as well, and we need to define the unknown pressures. So condenser pressure is 0.2 atm. Okay, and then reboiler pressure is 2 atm, and then finally it requires the external reflex ratio. So it has already calculated the minimum reflex ratio, that is 2.301. So we already know that the external, as we can see, we have defined here as external reflex ratio as 3, which is obviously greater than minimum reflex ratio, so everything is okay. So it turns out to green, and it is showing the message of okay. So now we can go to the rating and worksheet, or many other things we can find here, like distillation, flow rate, and bottom flow rate, and we can find like reboiler duty and condenser duty, and many other things. So the important thing is under the tab of performance. So here we need we can find like minimum number of stages, actual number of stages, optimal feed ratio. So these are the two particular important information, so we can utilize it as round of numbers, like 10 as a feed stage, and 18 as number of stages. So now let's move to the actual distillation column. Here you can see, now drag and drop it here. Okay, and now we can either copy this stream. Okay, so we can rename it as F. Okay, so it is quite alright, like it is green and with the OK message. So now we can double click here and go to the distillation column, and we can define it as distillation column. Okay, so feed here is F, and the number of stages like we calculated in the shortcut design, these are like 18, and like feed stages 10, and here we have like stage numbering. We can either go with the top down, or we can go with the bottom up. So we are moving with the top down approach, and we can here define condenser duty as Q_CON, and we can define the reflex reboiler duty as Q_REB, and we can define the bottom as B stream, and we can define the condenser as total condenser, and with the overhead product flow rate as D. Okay, so now we can see like it turns, we can move to the next tab. Here we have in total 5 tabs, so we will be moving to the second tab. So here we have like many types of reboiler configuration, so we will be moving with the ones through reboiler. We can choose either as a circulation without baffle and with the baffle as well, so we are moving with the default function. So by clicking the next, we move to the tab. Here we need to define the condenser pressure, that is 0.2 atm. Okay, and then we have the boiler pressure, that is 2 atm. So for the timing we can ignore this pressure drop in the condenser and the boiler, so we can move to the next, and these are like optional temperature estimates, so we can neglect it for the time being. So moving next, we have reflux ratio of 3. All right, okay, so we are done with here. All right, so here we go. Like it is still unconverged, so we need to move to the monitor tab. So here we have only defined one specification, that is reflux ratio, that is 3. We can uncheck this because we have not defined any of these specifications. So we need to define one specification so that degree of freedom becomes 0. So for that we need to move to the tab spec. Okay, so here go to add, and here we have many specifications. So since we know the column component fraction, so we need to click that. Okay, add spec, and then we can go to the stage that is from the condenser, because it is the top product, so it is mole fraction. All right, everything is fine. So spec value is 2 mole percent, so 0.02. So it is for the component toluene. Okay, so everything is fine. So now we can see we have a component fraction here. So now we need to move to the monitor. Okay, so here everything is fine and the degree of freedom becomes 0. So we can now run. So you can see it is converged, and it turns out to be green. So now we can go to the parameters. Here we can see pressure with the tray position. We have many info like temperature and flow rates along with the pressure for each and every tray. So we don't have any side options. So let's move towards the internals. Okay, so there are no internals as of now. So as we can see, internals input incomplete. So we need to add the internals here. Okay, so by default it is taking the sieve tray along with the default tray spacing of 0.6. So now it is showing that internal calculations complete with the errors. So we need to go to the hydraulic plots in order to identify the which sort of errors are there. So view hydraulics. Okay, so now we can see there are some errors here at the tray 1 and tray 17, and there are some warnings. So for the time being we can ignore the warnings indicated with the yellow color, but we need to address these warnings indicated with the red color. So now let's move towards the tray 1. So here we can go and click here. So it is showing that the entrainment at the stage 1 is above the maximum limit, so it recommends we need to increase the tray spacing. Alright, so now we can move to the other warnings. Here it is showing operating point is approaching the weak point, but it is inside the limit, so everything is alright, fine. Here we can see operating point is within this range, within this curve, so it is okay, but there is some danger, but everything is fine for the time being. So we can move to the tray 17. Okay, so it is saying that there is some whipping at the stage 17, so we recommend decreasing the number of holes, caps or valves. So okay, so we need to either change the tray type, so we can move to the caps or valves. Okay, so here you can see it is lying on the edge of the this curve. So okay, so let's go to the internals, and then we can change the trays type. So we can change it to the bubble cap. Okay, so now let's go to the view hydraulic plots. Okay, so now you can see the warnings at the bottom are gone, and but we are still facing warning at the tray 1 and little bit warnings here at the other some top trays. So we can ignore these sort of trays, but for this warning, since it is lying outside the region, so it is showing that we recommend increasing your tray spacing. So okay, so let's try to move to increase the tray spacing to 0.8. Okay, so it is still over there, so let's try 1. It is still there as warning, so let's move to the 1.2. Okay, so still at the tray 1 there is warning, but for 3-4 stages warning is gone. So it shows that by increasing the tray spacing, the warning at stage 1, which is the due to the entrainment, so it is not being covered. So we can stick with the default tray spacing as 0.6, because with the increasing the tray spacing we are going to increase the column length, and which obviously comes at the cost of the capital cost. So it's okay, we can go with like entrainers at the top of the first stage, which can minimize the entrainment to some extent at the industrial level. So we can stick with the 0.6 the tray spacing, because everything else is fine for the time being. So now we can go with the view internal assembly, and here we can find like a total height, like head loss, pressure drop, each and everything we can find here. So it is showing like it is bubble cap, which as we already checked previously. Here you can find the many information like bubbling area, downcomer area, and many other things. You can find it here, which you can see like during the manual calculations. So that's all regarding the design of distillation column. So I hope I covered everything in detail, like internal design and starting from the shortcut design to the regress designing. So